7.1 talks about trigonometric identities. So we have the identities that we've been using all along. We want to make use of those in this section before we move on and add to them. The fundamental trigonometric identities consist of the reciprocal identities, and we're aware of those. Sine is 1 over cosecant, cosine is 1 over secant, tan is 1 over cotan. Tangent has a bonus, is sine over cosine, and of course the other way around as well. Now, Pythagorean identities are going to be key. Sine squared of an angle plus cosine squared of an angle equal 1. If I divide this equation by cosine squared, sine squared over cosine squared is tangent squared, cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. And if I go back to that equation and divide everything by sine squared over sine squared is a 1, cosine over sine squared is cotangent, and 1 over sine squared is cosecant squared. You could derive that anytime you need. Fairly simple to do. But those are important because anytime you see a square, you should be thinking probably it's one of those. And there is even odd identities. Cosine of theta is the only even function. Cosine, of course, and associated with cosine is the secant. And the rest are odd, which means if you throw a negative in, an odd function will move it out. So multiply the x by a negative, that ends up multiplying the y by a negative. That's true for sine and tangent. Cosine is the only function, and secant, of course, that absorb the negative because they're even functions. Keeping that in mind, what you're doing here, it's kind of like a puzzle. Verify the identity. They give you the answer, they want you to get there. So we make use of this. Verify the identity. We want to really take the side that seems to be more complex. In this case, that seems to be the left side. We want to work with the left side to make it the right side. Now you can't play with both sides. It has to be one side. So when I look at a problem in this section, I'm looking for one of two things. Are there squares or are they linear? If they are squares, then I'm going to be dealing with this because it has to be the Pythagorean identities. And if they're linear, I'm going to use this. Now, anytime I'm stuck, I write everything in terms of sine and cosine and use algebraic manipulation. And that's really what it takes. So when I look at this, I say, okay, you know what? I'm going to work with the left side. This is the cotan of x times 1 over cosecant of x. Cotan of x is cosine of x over sine of x. And this is the sine of x. Those cancel out, and I'm left with the cosine of x. And once you get the right side, you would know that you are done. So again, it's like a puzzle trying to figure out how to do this right. So you look at both sides of the equation and you have many options to start. I'm looking at this problem and I'm thinking I could start with the right, I could start with the left. It doesn't really matter. It's up to you. So if I glance at this, if you decided to work on the left, keep in mind I know the answer is this. So I know where I'm going with this. If I start with the left, I say, okay, the right doesn't have any squares. This is not a square. This is not a square. And those don't combine. But the most use of sine squared of theta plus cosine squared of theta equal 1, which is this identity, is for you to use the sine squared would be 1 minus the cosine squared, and the cosine squared is 1 minus the sine squared. That's mainly how you use it most of the time. So sine squared is 1 minus the cosine squared of u divided by the cosine of u. Again, I notice these are two separate terms, so algebraically I could split this up. So I make use of the right side to my advantage because I know what the answer should look like. And 1 over cosine is the secant, and this cancels with one of those, and there it is. It looks fairly simple if you know what to do. And eventually you'll get there by doing enough problems. Now, if I glance at the third example, I notice that we have, on the right-hand side, that's a 1. So, obviously I have to work with the left side. This is the cosine, use a darker color. This is the cosine of x times 1 over secant of x plus sine of x times 1 over cosecant of x, right? So this is cosine of x, and this right here is cosine of x. This is sine of x, and we know 1 over cosecant from the reciprocal identity up there is the sine of x. So you can only work with one side. This is cosine squared of x plus sine squared of x, and we know cosine squared plus sine squared is a 1. It's right there. So, kind of fun, I don't know, I think. Students don't like identities because there's so many of them. Well, you play with those enough, you'll get the hang of it. So, I look at part D and I notice the right side is a 1. There's not much to do with the 1, so it has to be the left side I'm going to play with. Well, the top is already set. The top, not much I could do. The denominator, I could FOIL. If I FOIL that, that's the first squared plus twice the product of those plus the last squared. And anywhere I see a sine squared plus cosine squared, that's probably the most famous identity of them all. That's a 1. And any quantity over itself other than 0 is a 1, and there it is. And that's really how complex these are. It's not really hard, it's just different, and you gotta adjust, and that's why I'm breaking this into literally 2 separate pieces. I want to get this first section out of the way before I start 7.2, so I'm going to jump to 7.4, give you time to finish this before we tackle the second set of identities. Altogether we have 3 sets. This is the first one. Here I'm glancing at this and something looks odd. This says if you subtract those, that's the same thing as you multiply them. That sounds kind of odd. Well, let's see if that works. Your choice. You want to work with the left or right, it makes no difference. Whatever you want. It's up to you. So if I decided to work with the left, I say, okay, well, that's multiplication. So I need to somehow combine those. I could say that is the sine squared of t over cosine squared of t minus sine squared of t. Right? And the reason I'm going for sine and cosine, because I want to factor a sine squared out of it. That's the only way I can get multiplication. If I factor a sine squared out of both of those, I'll get 1 over cosine squared of t minus 1. So the sine squared I got, that's half of the problem. Isn't this secant squared of t minus 1? And if I look at the square, secant squared is right there. But I have secant squared minus 1. Secant squared minus 1. Isn't that tangent squared? There it is. Now, any of these problems, you want to see me working the right to get to the left, ask me during the class discussion and I'll be more than happy to show you. If I have time, I would do it. Just I have quite a few of those to tackle. So, how about the next problem? How about F? Those look somewhat confusing. The worst thing you could do is move things from one side of the equation to the other. Verify identities, you work with one side of the equation and only one. Let's say I'm going to play with this. Again, I look at the right side. I notice there are no cosines. There's only sine squared. Well, I know how to do this. I know how to get rid of cosine anytime I need. Cosine squared is 1 minus the sine squared of x. If you distribute that in, that is 2 minus 2 the sine squared of x minus 1. And 2 minus 1 is 1 minus twice the sine squared of x. And since I got the right side, I'm done. And looking at those, I could work with the right side or the left side, but it seems the left side is more straightforward in the sense there's only one thing to do. Distribute. That's one way. Or, it's up to you, or write everything as sine over cosine and see if you can get that. It's up to you. Meaning, I could say this is 1 over the cosine of v times 1 over the sine of v. And I could say, but those are sine of v over cosine of v. And this is cosine of v over sine of v. So you have many choices to do, and all of them will lead the same way. Cosine of v, sine of v. If I get a common denominator, I could say that's the cosine of v, sine of v, and this is missing a sine of v, and this is missing a cosine of v. So that will be a sine squared of v plus cosine squared of v. That would be a 1 over, so that's a 1 right there. That will be a cosine squared of v, sine squared of v. And that would be what? Oh, I miswrote that one. I'm sorry. That's what I mean. Sorry. And that would be 1 over cosine is the secant squared of v, and 1 over cosine squared is the cosecant squared of v. So you work with one side until you get the other side. I made those up, so some of those I miswrote. Alright. The next problem down on the list. Looking at those two and thinking, which way should I go? Should I go this direction? Should I go this direction? It's up to you. Again, you could work with the right side if you wish. It doesn't matter. It's up to you. You could work with the left side. It makes no difference. So, if I worked with the right side, I could say, and the reason I choose the right side because it's hard to see this when you work the left side. If you clean the left side out and play with that, it's very hard to see a tangent over 1 minus tangent squared. But if I write tangent as sine and cosine, I could see this easily in terms of sine and cosine. So this is sine of y over cosine of y over 1 minus sine squared of y over cosine squared of y. And this is a complex fraction. All what I need to do is make sure they all have the same denominator, which is cosine squared. This is missing a cosine squared, multiply top and bottom by that. This is missing just a cosine, multiply top and bottom by that. If they all have the same denominator, they cancel out because you multiply by the reciprocal, and that's going to cancel. That's going to be sine of y, cosine of y, and the denominator will be cosine squared of y minus sine squared of y. And since this is what I have on the other side, there it is. And here again, I notice there's only a cosine squared here. There's sine and cosine on the left. So I know which way to go. I would work with the left side. I would say tangent is sine of x over cosine of x Cotangent is the cosine of x over sine of x, all over sine of x over cosine of x, plus cosine of x over sine of x. And I noticed that the LCD is cosine of x, sine of x. So this is missing a sine. This is missing a cosine. This is missing a sine. And this is missing a cosine. So since they all have the same denominator, I ignore it because when you multiply by the reciprocal, that cancels out. The top will be the sine squared of x minus cosine squared of x. The denominator will be the sine squared of x plus cosine squared of x. Well, I am on the right track because the denominator is a 1. But I noticed the right side only have cosines. So I get rid of this sine squared by saying that is 1 minus the cosine squared of x. And that would be 1 minus cosine squared minus cosine squared would be 2 cosine squared of x over 1. Okay, the last example of these types, I glanced at this again. I noticed the right side only has sines, the left side cosecant. So probably I start with the cosecant because I know that I could write a cosecant as 1 over the sine of x, 1 over the sine of x. And if I look at this problem, I notice that the LCD for the top and the bottom is sine of x. So I multiply top and bottom by that. And what I'll get, if I ignore the denominator, because when you multiply by the conjugate, by the reciprocal, they cancel out, just read the top. Those were called complex fractions in your previous class. And there it is. That takes care of this problem. Now, I have a new set of directions. Let me see if I could fit it there. Yes, I can. Very good. Okay. If I need more space, I'll go down and do it. Make the indicated trigonometric substitution and simplify. So that first example, and this would be example 2, right? Yeah. Substitute. So take this value and put it right there. This is something that you have to do in calculus. And since it's trig based, I want to get it out of the way right here. Replace that x by sine of theta. The idea is to get rid of the radical. Second semester calculus. 1 minus sine squared is the cosine squared of theta. And the square root of cosine squared of theta is the cosine of theta. It should be an absolute value, but we restrict theta so that this is always positive. There. Okay, it doesn't like to play. No problem. Let's look at the next problem. The next example, we have again another replacement, but here I'm going to make the replacement in 2 places. I'm going to take x, replace it by 4 secant of theta. So this will be 4 secant of theta squared minus 16. Remember what the goal of this whole thing is. Eliminate the radical. That's the purpose of all of this is. So this is 4 secant of theta. I just carry along. The top is going to be 16 secant squared of theta minus 16. That would be the square root of, if I factor a 16 out, that's the secant squared of theta minus 1 over 4 secant of theta. That is the square root of 16, and secant squared of theta minus 1 is tangent squared of theta. And that would be a 4 tangent of theta over 4 secant of theta. This is sine of theta over cosine of theta. and secant is cosine of theta, and I'm left with a sine of theta. And that concludes this section.